quite stable. And essentially what happens now, check it out, the ligand comes in, we have a cis-trans isomerization, the requirement for the reductive elimination, the two groups need to be mutually cis, and the two ligands that were dissociated in the starting of the cycle rejoin, and we close the cycle and generate the silylated product. Now, we do have side products in hydrosilylation quite often, and here we sort of see what happens. If we start with a palladium 0 species, let's start here at this point, which is the starting point in the cycle typically. We can have the oxidative addition, right? We can have the competitive or coordination of the displacement of the ligand and simultaneous coordination of the alkene. And what can actually happen then is, instead of having a reductive elimination, what we actually have is a insertion into the platinum silicon bond, and we form something like this. Do you guys see that? And what can then happen is we can have a beta hydride elimination to form this product here, which is not the desired product. Whereas here, what do we have? We actually have we have insertion. Check this out. This is a key point in the classic chalk-Harrod mechanism. We have insertion of the alkene into the platinum hydride, right? That hydrogen originating from the H on the silicon. This has been secured by deuteration studies, incidentally. And then we have the reductive elimination. So insertion of the alkene into the platinum hydride, cis-trans isomerization as required. If not, it goes straight through reductive elimination, we get the product. What we have here is insertion of the alkene into the platinum silicon bond, which is also possible, right? Now, the insertion into the platinum silicon bond is, of course, going to be much slower kinetically than the insertion into the metal or the platinum hydride bond. Why? Well, because it's bigger. This is a bigger substituent. Well, that's a simple way of looking at it. Also depends on electronics, but I mean, it's obviously also going to depend on the nature of these R groups here and their size and whether they're electron rich or electron poor and all these factors. But this is a side product that one often obtains in the hydrosilylation of alkenes. But this is the desired product, right? The hydrosilylated alkene. Now, concerning the chalk-Harrod mechanism, which we've just looked at, which is basically what I've represented here, we have a so-called modified chalk-Harrod mechanism, all right? And I think basically one can look over this. I don't think that we should really discuss this at this time. I'm really just interested in the chalk-Harrod mechanism. But one can look over this and you can actually see that it's possible to obtain other products using this competitive pathway over here. And the great thing is, I'm not even going to go over this, because you can actually look at this and figure it out, I think by now for yourself, what's happening in each of these steps, right? Can I say that with confidence? Well, let's do it together. Maybe we should, just to see if I'm right. All right, this is the chalk-Harrod mechanism. Okay, this is the chalk-Harrod mechanism here, essentially. Let's now go into this cycle here, this competitive cycle. What's happening here? Beta hydride elimination, yes. And what's happening here?
No, it's like an exchange.
Exchange. It's not an elimination.
That's an alkene insertion.
It's not an alkene insertion and an elimination. It's not an insertion, be careful.
Yeah.
It's just a competitive coordination. This alkene, which is coordinated, is displaced by this ethene, and you get this guy here. And what's happening here?
The insertion. No, the coordination.
No.
No, it's insertion and then, yeah.
Insertion and reductive elimination.
Oh, that's
Alkene insertion into the methyl hydride followed by reductive elimination in one step. Now, here we have oxidative addition. Right, let's look at this again. Oxidative addition, coordination. Notice I've left the ligands away. They're going to coordinate and decoordinate as required. Coordination, insertion into the metal silicon bond, reductive elimination, we get our product. Or we have coordination, insertion into the metal carbon, the metal hydride bond of the alkene, check it out, and then reductive elimination. But we end up with the same product. Okay, so that's sort of the whole picture in hydrosilylation. Now it's possible, of course, to do, again, we're talking about this business of prochiral alkenes, remember last week. What does the word prochiral mean? As a substrate that in one step can be converted to something chiral in one synthetic step. So of course, if you have an alkene like this, and you hydrogenate it, that carbon atom has the propensity, may be chiral. Let's say not hydrogenated, because then you're going to have two hydrogens. But if you, let's say, brominate it, this is going to be a chiral center, i.e. that is a prochiral alkene. So of course, people have developed stereoselective alkene hydrosilylation catalysts. This is an example, SMEO-MOP. And this guy, used in conjunction with palladium, under hydrosilylation conditions, will form stereoselectively this stereoisomer here. Now, remember what I said to you earlier, hydrosilylation is adding value to cheap alkene feedstocks. Here you see it. Because basically, if you do hydrosilylation with trichlorosilane, which is quite a cheap feedstock, incidentally, you get this or this. Now, it's very easy to convert silyl groups to alcohols, which are much more of a much higher value. Particularly something like this, which has got stereo center built into it in 90% enantiomeric excess. And of course, that's important because remember, this whole business of building chiral molecules comes down to generating chiral centers. And here's a way of using hydrosilylation. Very similar to what we discussed last week, incidentally, right? In a way. Now I just want to briefly mention ketone hydrosilylation. So of course it's possible to hydrosilylate alkenes, that's the classic thing. It's also, however, possible to hydrosilylate ketones, which we see here. And again, here stereoselectivity is key. Now there are really absolute plethora of catalysts that hydrosilylate ketones. Ketone hydrosilylation is kind of done and dusted, right? And if you want to publish something in ketone hydrosilylation these days, a new catalyst, you better be sure that it does the hydrosilylation in a stereoselective way. Amazingly, I published something in JACS which was not stereoselective, and I accepted it. For ketone hydrosilylation, I was lucky. But it was because the catalyst system was very novel. Anyway, ketone hydrosilylation, the benchmark systems do asymmetric hydrosilylation of prochiral ketones, and these are some examples, in fact some of these we've seen in an earlier lecture, of ligands, they're called pyridine oxazolines, that when coordinated, for example, to iron or palladium, will do the ketone hydrosilylation in a stereoselective fashion. Now, the mechanism, this is just an example of a rhodium system that does hydrosilylation. Basically what you do in hydrosilylation is you have the silane and you have H sitting on the silane, for example. And the mechanism is as follows. Basically, the ketone coordinates to the metal. I use rhodium here as an example, but there's a great many complexes that do the hydrosilylation, including iron. In the meantime, you have a sort of a side-on coordination. Okay, look at what's happening here. You have a migration of the silyl group onto the oxygen with coordination, or sorry, sigma bond formation between the rhodium and the carbon atom, which is electrophilic. And then what you basically have, look here, is you have a sort of a hydride elimination. Well, it is a beta hydride elimination to form this product here. Now that's not the desired product, right? This is a side product. The desired product is this guy here. This is a side product. So how do we get that product? Well, you get it like this. So if you imagine that this is now the intermediate, you can have one of two things happening. You can either have a beta hydride elimination, which is of course going to afford this product here, or you can simply have a reductive elimination of this whole thing here, and you get the desired product. So ketone hydrosilylation in a nutshell, coordination, silane activation in a second subsequent step, silane activation, you form an intermediate that looks like this, right? Like this, if you will, basically, and then you get hydride elimination or reductive elimination to form the desired product. The interesting thing about ketone hydrosilylation is, in fact, that it occurs in a concerted fashion. So, well, not always, but one of the proposed mechanisms is that it doesn't occur in a two-step fashion, but in a concerted mechanism. In other words, look at what's happening here. We have the silane, we have the ketone. They approach the metal and they form this five-membered intermediate. And in a concerted fashion, you form this thing here, and then you form the products. If it goes via a two-step mechanism, you first have oxidative addition of the silane over the rhodium center, and then coordination of the ketone. It's just two different mechanisms to arrive at the same point, right? And then once you've arrived at this point, either in a concerted or a non-concerted way, you either get beta hydride elimination or you get reductive elimination to form the desired product. And of course, this process, using very similar arguments to what we had last week in terms of the L-DOPA synthesis, can be employed again to predict how the alkene is going to approach the metal center and whether you're going to get R or whether you're going to get S. The same things that you can use as Knowles used in predicting how L-DOPA was going to be synthesized, you can use in this case. So that's ketone hydrosilylation in a nutshell. We're going to take a 10-minute break. Well, before we do that, any questions? What?
Why do you say asymmetric? Like, isn't it going to be asymmetric?
Asymmetric, no. Asymmetric means that you're doing catalysis where you end up with a chiral center. Asymmetric catalysis means that you're doing catalysis in a way that you end up with chiral products, and that you have a chiral center, and you want to do it in a way that you get a high enantiomeric excess and not a racemic mixture. If you get a racemic mixture, it is symmetric. If you get a high selectivity towards, let's say, the plus or the minus or the R or the S, the L, or whatever convention you want to use, it's asymmetric. So when I talk about asymmetric catalysis, I'm talking about chiral catalysis.